In this video, I'm going to talk a little bit about integrating vector fields over a surface, show you the formula that we're going to use for it, and then just work a couple of quick examples to introduce this idea. And then in a later video, I'll talk a little bit about a really important theorem that's going to apply this idea that we're talking about here. So let's go ahead and get started. So when we're integrating a vector field over a surface, our setup for it is going to look really quite similar to kind of like integrating a vector field over a line, except now instead of working with a line, we're now working with a surface, which means area in 2 dimensions. So we're going to have a double integral this time over a surface. But we still have this idea of our vector field being dotted with D, and then we have capital S with a little vector arrow over the top of it to denote that we're kind of trying to think about our surface as being, in some sense, a vector or having some direction to it. And the way that we're going to want to take this integral is going to be quite similar to how we talked about surface integrals previously. And so we still have this double integral over the surface, and we have f evaluated at r of u v dotted with in and then du dv. And in this particular piece right here, r of uv is a parameterization for the surface S, and n is equal to r sub u cross r sub v from that parameterization, just like we had it in our last video on this, or at least in our last video on surface integrals anyway. So a lot of these pieces are staying the same as in our previous video. We're now just trying to incorporate them into working with a vector field. And if we want to think about this intuitively, what's going on here is we're looking at our vector field and saying how much the vector field has in common with the direction that that surface is pointing. So how much vector field has in common with the direction the surface points. Because this normal vector here, this n here, is really actually it's just normal to your surface, which means that it's pointing out and away from your surface. So what you're really kind of trying to track here is how much of your vector field is actually flowing through your surface. So, I mean, there's a lot of different visualizations that you can use for that. You can think about current passing through something, or water going through like a sieve or something like that, or, you know, fish swimming through a net. But basically the idea is you have something that's moving in a certain direction, and that's your vector field, and is passing through the surface. And so because we want to figure out how much those two have in common, that's where this idea of having a surface pointing in a particular direction is concerned. Now, something that I should say is that your normal vector may need to be swapped directions depending on whether we want to consider an outward pointing surface or an inward pointing surface. So I will note that this may need to be multiplied by -1 to fix direction. And that's okay. You just have to take a look at this vector and say, okay, was I told that I want things to point inward or outward? And then just check to see, okay, does this actually point inside or outside of my surface? And if it's pointing the wrong way, no big deal, multiply by -1. So, but yeah, that's pretty much all there is to it. Let's start working some examples. So our first one, we are going to compute the integral over the surface S of f dot ds, where S is equal to x, y, z, such that x squared plus y squared plus z squared is equal to 16. And we have that z is greater than or equal to 0. So in this particular case, we've got that we're looking at like kind of like a sphere, so I can kind of sketch that really quick. And one thing that I do want to emphasize is that since we're looking at a surface, and that since we have this equal sign right here, we're only looking at kind of the shell of the sphere. We don't really care about the interior of it at all. We're really just looking at the outside. So here, this will be our sphere. And since we only want the upper half, I will just draw the upper half. So that's the shape that we're looking at. And we're also told that we want it to have the orientation. So the unit normal points upward. And we are also finally given some information about our vector field F, and we're told that F is equal to 2y plus 3, and then x plus z plus 4. Oops, there we go. Okay, so let's talk a little bit about that orientation. So when it says that the unit normal is pointing upward, what it really means is that we want to consider kind of like the outward facing portion of, well, just this surface, okay? So we want to know what's happening as we're moving outside of this here. So we're going to be looking at kind of going in this type of direction is really what that means. So otherwise, sometimes we'll talk about inward pointing, which means that all these arrows would then be pointing to the inside of our sphere there. So, and it's really not even a sphere per se. It's really just kind of like the shell of our sphere. Again, it's not including the inside or anything like that. It's really like, so for example, we're considering a balloon that's full of air, and we just want the balloon itself as opposed to, say, something solid like a balloon full of water or something like that. Okay, so our shell here is empty. We're only considering the surface. So anyway, let's go ahead and start jumping into computing this integral. So we know that our double integral over s f dot ds is equal to the double integral over s of f of r of u v dotted with n and then du dv. So I really just, the big thing to compute here is going to be r, and then the rest of it should follow pretty naturally. So r of u v is going to be equal to, well, since we're working with a part of a sphere here, really the best thing to do is going to be to use spherical coordinates to be able to do this. So what we're going to get is going to be 4 cosine of u sine of v, and then 4 sine of u sine v, and then we have 4 cosine of v is what that winds up being, because the radius of our sphere is equal to 4. And then we have these pieces right here with the cosine u sine v, sine u sine v. Those come immediately from our spherical coordinates identities, as does that last component there. Now, since we are wanting our sphere to go all the way around the circle, we're going to have u, which is kind of acting as our theta here. That one, we need that to be between 0 and 2 pi. And since v here is holding the role of phi, and we're starting up here at the top and going down only halfway, we need phi or v, I guess in this case, to be between 0 and pi over 2, because again, we only want it to come down halfway. So these will give us our bounds for integration. This is our parameterization that we're going to use to plug into our function or our vector field there. Now, in order to get our normal, we need n, which is equal to ru cross rv, which I'm going to kind of leave the details of this up to you, but what you get out of that is going to be a negative 16 cosine u sine squared v, negative 16 sine of u sine squared v, and negative 16 sine v cosine of v. Okay, and I think we've actually gone through a computation very similar to this before. So now we want to check to make sure that this normal vector is actually pointing in the proper direction. We want it to be pointing out and away from our surface. So I'm going to kind of imagine, all right, what happens if I plug in, well, I probably don't want to plug in 0 because I'm just going to get a bunch of zeros, and that's not very enlightening. But we can plug in, for example, I don't know, just like pi over 4 or something like that. And we're going to look at being in our first quadrant here. So if I plug in pi over 4 into each of these, what I'm going to wind up with is, well, cosine at pi over 4 is positive, sine at pi over 4 is positive. Same idea here and here. So since each one of these, if we ignore the negatives, are positive without those negatives, once I have those negatives there, then everything's going to be negative, which means that my n, as I have it written, is going to be pointing back inward more like that, okay? So this is what I found, and that's not really what I want. So to fix that, I just need to multiply it by -1. So we multiply by -1 to fix the orientation that we found here. So not a big deal. You just have to make sure to double check and then multiply by a -1 to correct. Okay. So anyway, I think we are actually just about ready to go ahead and plug things in to get our integral. So our integral I is equal to the double integral over, probably want to write this a little bit differently. So integral from 0 to, let's see here, we said our bounds on v are going to be from 0 to pi over 2. Our bounds on u are from 0 to 2 pi. And then f at r of uv is going to be, looks like I've got 2 because there's no x there. Y plus 3, so that's going to give me 4 sine of u sine of v plus 3. And then I'm going to have, oh, I'm going to run out of space here. X, which is 4 cosine of u sine v plus 4 cosine v, therefore z, and then plus 4. And then this is dotted with my vector for n, which was the -16, except now I need it to be positive because I have to correct the orientation. So 16 cosine of u sine squared v, 16 sine of u sine squared v. Oops, that should not end there. And then 16 sine v cosine of v, and then du dv. And so, yeah, and that looks like that's really pretty much it for setting up that integral there. So after that, it's really just a matter of going through and taking this dot product and computing the integral in each one of the little pieces, which I'll kind of leave to you. But the main point of this is really just seeing how it all fits together and seeing all the different pieces and stuff like that. So if you want to know the numerical answer for this, you can really just throw it into like an integral calculator or something like that if you really wanted to. So yeah, okay, so that's kind of the idea. Let's look at one more example for this. Okay, so in the next example, we're going to find the double integral over s of f dot ds, where this time our surface is going to be equal to the set x, y, z, such that z is equal to x squared plus y squared, and z is less than or equal to 36. And our orientation is going to be so that it points downward. And we're told that our vector field F is equal to x plus 5, 0, and y plus z plus 7. Okay, so let's take a quick look at what our surface is here. So we've got z equals x squared plus y squared, and z is less than or equal to 36. So this guy right here, that's just a paraboloid. And we want z to stay less than or equal to 36. So we're looking at this right here. Our height is 36. Okay, and we want it so that our unit normal points downwards. So we want it to kind of ultimately point out like that. We'd have arrows that come out at us, like so. Okay. So this is our surface. That's the kind of orientation we want, where all the arrows are pointing outward or downward, I guess, in the description. So we know that the double integral over sf dot ds is equal to the double integral over s of f r of uv dotted with n du dv. So we just got to find this parameterization here and then use that to get our normal vector n, and then we're ready to set up our integral. So since we've got this kind of like z that's here by itself in both places here, and we have the x squared plus y squared, we're going to use cylindrical coordinates to parameterize. So we are going to have r of u v be equal to u cosine of v, u sine of v. And then the height on here for our z component is really just given by u squared, right? Because this guy right here is just u squared. So, and then in this case, because v is kind of acting like our angle or our theta in this case, and we want it to go all the way around the circle, we need 0 less than or equal to v less than or equal to 2 pi, because I want it to go all the way around. And then I need u to range anywhere between 0 and, well, I guess up to 6 right here, because this guy right here tells me that u squared is less than or equal to 36, so u has to be less than or equal to 6. So these are going to give me my bounds of integration for this right here. Okay, so now I need to compute n, and computing n this time is actually a lot easier than the previous time. So I'll once again leave the details of that out though, but the main idea here is that you're going to take the partial derivatives for u and for v, take the cross product of those guys, and ultimately what you're going to get from that is going to be negative 2u squared cosine of v, and then negative 2u squared sine v, and then u in your final component there. Okay, so now it's time to consider, okay, did we get the right orientation? And I think that the biggest way to, or the easiest way in this case to look at that is going to be, we have this u that's isolated right here, and we really just want to check to see if it points up or down. So u right here, since u is always positive, we know that this is always going to have an upward direction to it. It's always going to have an upward component because our z component is always positive, which means we're always going up. Well, we don't want that. We want to go down. So we multiply by -1 to fix that. Okay, great. So now we're ready to go ahead and set up our integral. So we've got I equal to the integral from 0 to 2 pi, integral from 0 to 6. And then we have, we've got to replace the pieces of our vector field using our parameterization here. So I'm going to have u cosine of v plus 5, 0, and then u sine v plus u squared plus 7. And then I'm going to dot that with my normal vector here, which is now going to be multiplied by -1 to correct. So 2u squared cosine of v, 2u squared sine of v, and then -u, and then du dv. Yeah, and then to compute that integral, you just take the dot product, do the integral as normal. Again, it might be a little bit tedious. If you want, you're welcome to throw it into an integral calculator to see what the actual numeric answer of this winds up being. But I mean, the main focus of this here is really just the process that we went through, and that we have this really nice formula right here that is actually structurally quite similar to what we've worked with in the past. And we just have to find the parameterization, find our normal vector, maybe flip the normal vector around depending on which direction we're hoping to have our surface face. So like, for example, here, if we'd wanted our vector to be pointing upward, then it would have been fine as it was, because we would have had u saying, okay, u in the third component here means that everything's pointing upwards as opposed to pointing downwards. So that would have worked out fine. But we wanted it to be downward. You always want to make sure to double check that you got the right thing out of it. So yeah, and I guess one thing that I do want to point out, a really common question that I get is, how do I know if orientation matters? Orientation matters anytime that you're not taking the length. If you're taking the length of n, then we don't care about orientation. That negative is just going to disappear in taking the length. But anytime that it's not going to get just kind of swept under the rug with that process, you know that orientation is going to matter. So you really just kind of want to make sure to double check that you set it up correctly. So yeah, that's pretty much it. Thanks for watching, and I will see you guys in my next video where I talk about the divergence theorem. So I'll see you guys then.